So this lesson is on the beginnings of how we solve second order linear differential equations with constant coefficients. Now before we get into techniques and so on, I wanted to just go over some basic ideas and begin to start thinking about how we would actually craft a solution. Let's first look at a first order equation. Say this is a simple version. So if we have y prime is equal to y from your differential equation, or so your calculus course, you know that then y is equal to e to the x. If you have other situations, you might have, for example, let's say candidate solution would be y is equal to e to the rx, where r is real. So then y prime is going to be r e to the rx. Okay? So you might have, in something like that, then you might have 2 y prime, or better still, just simply put r y prime equals y, and that would give you y equal to e to the rx. So we could have 2 y prime, and so on, and that would be equal to e to the 2x and so forth. So there's this non-ambiguous approach to it. And if we look at, and this of course is where we see the exponentials coming from, of course, because of this equality of derivatives here. Now, if we look at second order case, initially we think we're okay. We could say y double prime equals y, and then y is equal to e to the x. Okay, and so it seems initially, at least, that we are back where we started here, but not so fast. Let's suppose if we have y prime, or double prime, is equal to negative y, it's a little difference, okay? Because this would not be, if we had e to the negative x, then you'd have negative e to the negative x, and then you'd have e to the negative x. But this is distinct from negative e to the negative x. So it's not straightforwardly an exponential function. What else do we know? What function's second derivative is equal to the negative of the parent function? If we have y is equal to sine x, y prime is equal to cos, and y double prime is equal to negative sine. And so there you go. We've got an agreement here. We also have y is equal to cos, y prime is equal to negative sine, and y double prime would be negative cos. And that also agrees. So we could also have sine plus cos, in the same way that you could have e to the x plus e to the x. Or we could have, for example, let's see here, if y is equal to e to the negative x, then y prime is equal to negative e to the negative x. Y double prime is equal to e to the negative x. That works too. So you could have candidate solutions so for y double prime equals y, you could have y is equal to...
Good afternoon, sorry for the interruption. Mr. Adams and Mr. Warden, please log into the staffing committee meeting at this time.
If we have this y principle here, y double prime equals y, then we could have a solution like this one, where we have both signs of the exponential function and it will work out. Similarly, we have y double prime equals negative y. This would give us y is equal to sine x plus cos. And you can affect the derivatives and get back to where you want to go with the negative sign present. Now here's the question of the day is, how can changing a mere negative sign move from an exponential function to basic trig? That's a good question, and we should be thinking about it. Now, if we recall our basic graphs, we have e to the x is going to be e to the 0 is 1. It's going to go like this, and this will be asymptotic to the x-axis if we go far enough. And so this is e to the x. And of course, say sine x is going to be some type of oscillatory function. And you could argue very easily that these two things look like utterly different concepts. But given this result, we have to accept that under the surface there is a connection that we were unaware of. Now, I'm not going to derive it for you because I don't have perhaps the time this semester. It is posted on my webpage in the aids, and you can certainly go look at the derivation there. So I'm going to introduce to you Euler's equation. And we have here e to the I theta is equal to cos theta plus I sine, where I is equal to the square root of negative 1. So here you have a combination of complex exponentials and trig, all in the same little spot here, kind of like a Rosetta Stone. Furthermore, if we do e to the I pi for a moment, well, cos of pi is going to be negative 1. And sine pi would be 0. So in this relatively simple expression here, you have exponentials, complex, pi, and negative numbers. Feynman, a brilliant American physicist, said this was one of the most profound equations in physics that he saw when he was in high school and studying on his own a little bit. Now, this applies to us because of how we're going to be solving these equations. So we're going to accept that there's some interesting things happening behind the scenes here, that these two radically different functions are basically similar, or cousins, and that the relationship between them is described in this case here for now. Now, this isn't complete, but it's a start. So let's see what we can do here about achieving a solution method our second order differential equation is a little bit easier than the first order. First, we have constant coefficients. So we have A, B, and C, which are real. So you may recall with the first order we had P of x and Q of x. There's none of that anymore. they are constants. Now, we may in time get a q of x, but there'll be, certainly a, b, and c will be only real numbers. And I described to you in an earlier video about what that means, where if you have our spring mass system, that the mass doesn't change, the spring constant doesn't change, and the viscosity or whatever of the liquid doesn't change. And those seem like pretty reasonable things, and we can do a fair bit with it. So the basic form is going to be a y double prime plus b y prime plus c y, and we'll use 0 for now, solving a homogeneous case. And this is important because the non-homogeneous case requires us first to solve the homogeneous case. So this is good work for us. Our candidate solution given all of this, okay, is going to be y is equal to e to the rx. Now there may be coefficients and so forth as well, but we would assume that our basic solution is this, and of course our coefficients would respond to that. So let's see what's going on here. So we would have y double prime, it's going to be r squared e to the rx. Y prime is equal to r e to the rx, and y equals e to the rx as our candidate. And so what you have then, by substitution, you would have ar squared plus br plus c quantity times e to the rx is equal to 0. Now we know that e to the rx cannot be 0 without it being negative infinity, which would be trite. So we can say that e to the rx is distinct from 0, and that means that our old friend, this quadratic equation, is going to be the only place where we can obtain roots. Hence, ar squared plus br plus c equals 0, and this is known as our characteristic equation. And so we need to solve this, and you solve this the way you've learned in grade 10 or grade 6 or whatever you learned about quadratic equations. And what we want to do here is to look at some of the consequences of these equations. So we have 3 possible solution types, let's say. And so we're going to have R1 and R2 will be real. So if we think about our quadratic formula, we have R is equal to minus b plus or minus the square root of b squared minus 4ac. Oops, let's get that right. There we go. All of it over 2a. So for this to be real, then this must be positive underneath here. And then you're going to get 2 different numbers depending on the plus or minus, but they'll both be real. And that's where we get an equation, a solution. I guess I rubbed it off. That'd be solution of the form y is equal to e to the r1 plus e to the r2. And there'll be associated constants and so forth, but that's not important. So we have that one form, and this is going to be some kind of exponential function. And so things that happen and slow down quickly would seem reasonable. Now, if we look at the two other types of solutions that can evolve from the quadratic, we have R1 equals R2, okay? And it's known as a double root. And it's in effect when the discriminant is 0. So, now in the case of physics, this is a singularity. Now, it's not that we can't calculate it, but what is it? It doesn't really serve much purpose. Because for the possible values that we're going to have given parameters and uncertainties and other things that are going on in our equations, the chances of this hitting the mark here, bang on, are slim to none. And so we'll just leave it for now. Okay? So this is not practical in every day. Now, of course, when you study second order equations in your math class, they will deal with this, and they'll compute the double root and deal with reduction of order and whatever else has to happen. But it doesn't serve us in our introduction here. Which leaves us then with the final case. And this is where R1 and R2 are complex. Okay? And so this means that b squared minus 4ac is less than 0. And when that happens, then an R will be equal to, let's say R1 is equal to A1 plus B1I. And we are also putting this entire exponent to a power, so we would have e to the R1. And this would equal to e to the A1 times e to the B1. And times I. Sorry, that's all I meant to say. E to the B1I. There we go. That's what I meant to say. So now we've looked at Euler's equation, but e to the A1 is a constant. So this is just going to be some constant c. E to the B1I is equal to cos b theta plus I sine b theta. So then our solution would look something like this. We would have, in this particular example, we would have, so e to the R1 would equal some c times this oscillatory function. Now, of course, when you're solving this, the solution, y is equal to e to the R1 plus e to the R2. And so we would have a more involved solution, which would look something like this. We would have, so y then would be equal to some, we'll just say C1 for now, and then you're going to have quantity cos B1 theta plus I sine B1 theta plus some C2 times cos B2 theta plus sine B2I. And now we combine and like some like terms and so forth. Okay, so, and you have to remember how you add, subtract your cosine functions and so forth and so on. And either way, the solution's result is satisfactory in so many ways. So we'll just say, simply put, we would have some constant quantity cos. We'll use another variable here for now, say k theta plus I sine k theta. Okay, collecting terms and messing around with the constants and so forth and so forth. But even if we have this, okay, this does not look like a sine function or a cosine function. You have a cosine function, okay, fine, but now we've got this complex function. What is all that? And what do we do? And it's a good question. We are indeed fortunate in all of this in differential equation theory, and I've said before, I present this to you without proof, because we're learning to drive the car, not learning how to build it. And what they're basically saying is if there are the coefficients of the dE, and in our case that's A, B, and C, are real, okay, and they are, and they'll always be real in this world, then we can use the coefficient functions of the solution. Which are also real. So then we can just simply default to cos theta plus sine theta. And so by this theorem, we can escape the whole issue of the complex function, which is very nice. But it's still not finished, because we don't know what this looks like. You have studied your math and so on for a little while, and cos plus sine doesn't mean anything to you. I have a second derivation on my webpage that I'm not going to do in this course again because of the time constraints, which will convert. But what we can say is that with a little bit of manipulation, we can show that this is equal to E to some coefficient there, either the AX times cosine BX plus some constant, which we can call let's see here, we'll call it phi for now. Now, in addition, you could have a magnifier function on the front here, say some, let's just make this a bit bigger. And this, of course, is the shape of the function you would expect. It's a single cosine operator. So if you imagine a guitar string or something like that, or spring, you stretch it, and then you let it go, and it goes, ooh, okay? So we're going to always take it to its maximum. So the nice part about using cosine is it's at the maximum when the thing is 0. Okay, so let's see where, so in this case, C and phi are computed using the initial conditions, okay? So your initial conditions, it'll be something like this, y of something is equal to something, and y prime is equal to something. So you'll have one that's going to be the parent function. Often when it's equal to 0, it's the easiest case. Doesn't guarantee, but often the case. And then the derivative. So you can then equate and sort out and decide what has to happen. But the nice part about this is that going through this whole process and getting to here allows us to understand what we're doing. Now, in the case of this class, while we're studying differential equations, I'm going to ask you to do the characteristic equation and figure it all out as you go. Solve for the roots, decide what it means, and all the rest. When we get a little further down the road, we can look at an equation and say, okay, it's going to be this, and we can move directly to whether it's this version or the other version, depending on the nature of the roots. And what you'll see here, the nuance of this, is let's suppose for a moment that we change the function to be one of time, which is more common anyway, okay? Now what happens here is, if this is, and A is often negative, doesn't always have to be. I think I should be careful here. because I don't want you to mix these up with the coefficients of the function. So let's rub these out, and we'll put in a couple of other letters. I will say alpha and beta, okay? So I don't want you to think that they're the coefficients of the differential equation, because they're not. There'll be some combination. So alpha is less than 0, and so when you have that, you have E is equal to alpha t, which is going to give you a damping, a reduction of amplitude. Now, in most equations, this one was homogeneous. There's no energy added. All we have is friction. So that generally tends to mitigate the amplitude of the function. So we start off with whatever, see, this will be basically 0, so this term is 1, so C carries the day, times all of this, and we can, for a moment, just keep it simple and make phi equals 0 for no phase shift. Then we're going to have a maximum. As time progresses, the e to this is going to make this a factor, which is going to be multiplied by the constant, which is going to reduce the amplitude of this function. And we call that a damped harmonic. So e to the alpha t cos beta t is going to look more like this. Now you can imagine this is a function that was pretty common in nature. Think of a shock absorber of a car or anything else. Ooh, you know, there's lots of that going on in many, many situations. Whether it's electronics with different types of devices or mechanical devices, this is going to be a very common arrangement. Now, the nature of this and the frequency and all the rest is a function of the coefficients, but that's secondary. So this is a way to look at what we call a damped harmonic oscillator. Now, in the course, the way I normally teach it, your second experiment is to assess the performance of a pendulum. And then you're dealing with this whole issue complete front on. I don't know yet. I strongly doubt we're going to have the time for that. But we'll have to see as this evolves as we get going with our COVID world. And so this allows us the solutions to these second order equations, which are a little bit easier in some respects than the first order ones, because again, we're not entertaining cases where the coefficients are functions. Now, again, this is basically the aspect of the math part of this course before we get into the applications of it, the true physics, if you will. Okay, so I'm just going to have a quick look here and see if I have anything else that I should be adding or subtracting here. I think we're all right for now. So that should get you going first with my lectures before on vector calculus, and then today's work on differential equations gives you the underpinning of the mathematics, also with the matrix work I gave you in June. So this allows you then to be able to solve various problems. So your homework, as I see it, would be to entertain yourself with the questions that are available. I've also published a section of textbook on differential equations as well. There's some more completeness there if you want it. And then, but the main point here is being able to solve these problems. I'm not going to give you, for the most part, calculus that is so difficult to do. The issue here is to learn how this works and how to apply it in particular questions, not to find ways to make the questions so difficult that everybody doesn't get them. I don't see how we're serving ourselves. I'm much more interested in you being able to interpret a question using constraint theory question, and then the effecting of the computation is in comparison reasonable. If you've forgotten constraint theory, I believe there's a video on the grade 11 page from last semester. You may want to have another look at that. I'm certainly going to be looking and showing approaching things as much as we can with that, given, especially in this course, where the problems are more difficult. Okay, so once again, if what we're doing here is interesting to you and worthwhile, please consider subscribing to my channel and or giving it a like and or a notification. I hope that in addition to serving my students right now, that other students interested in these types of things, this is another venue for them to hopefully improve their knowledge and so forth. Thank you for watching.